happy to see you. I'm glad you're back. Now we're getting back into learning here again. We've taken a little short hiatus from that. What are you going to learn? We're going to distinguish or learn the difference between vectors and scalars, meaning vector quantities and scalar quantities. Characteristics of vectors we're going to discuss, and we're going to talk about how to construct a resultant vector graphically. Scalars and vectors. A scalar shows magnitude but no direction. Magnitude meaning the number and maybe the units, but it doesn't have to include direction. Something could be going 30 meters per second. Which way? We have no idea. It's just scalar. They're just telling us it's going 30 meters per second. It's like an absolute value. 10 meters per second. It's still just a scalar. The displacement, we would give distance is a scalar. Displacement is not a scalar. Vectors. All right, vectors shows magnitude and direction. Sometimes that direction could be given with just a negative number, or we could start to include actual directions. 30 meters per second east, 10 meters per second west. These right here are examples of vector quantities. I also want you to realize that vectors are a lot of times represented by an arrow. And what I've done here is the length of the arrow usually represents the magnitude. So my first arrow here is 3 times as long as the one for 10 meters per second. Why? Because it's going 3 times as fast. The arrows are pointing in opposite directions because we would say to the right is east and to the left is west in this example. How do we distinguish the difference between them? Well, a lot of times in books, scalars are given to us as an italicized, and vectors are given to us bold. So when you're reading a scientific journal or a scientific something scientifically written, this is a good key to you whether or not you're reading a scalar or a vector quantity. Resultant vector. All right. We're going to start learning now what a resultant vector is. First, we want to make sure they have the same units. Meters and meters. Meters per second, centimeters, and centimeters per second. This second example here, this is an example of something that we could not put together here with our vectors. Why? Because the units are not the same. The second one is another good example of where students make lots of mistakes. We can't combine these because they're close, but it's not exactly the same. We've got a meters per second squared and a meters per second. So these two could not be added together. These vectors could not be added together. All right, adding vectors graphically. Well, typically what happens is what we want to do is we want to do what's called draw tip to tail. And on here, I'm going to outline the vectors here. We've got one vector here, and this is its tip. Down here is its tail. This is another vector that they've given to us. And I added them tip to tail because I always have a tip to its tail. I think I may have said it wrong here. This is its tail, this is its tip, and it's tip to tail. Up here is another tip. So I've added these two vectors together, and we could measure, all right, this resultant here. We could put our ruler on, like next to it, and I could measure it, and I could say that maybe it's 1, 2, 3, 4, 5, 6, 7 point, let's say 5 centimeters. And maybe that represents, maybe our scale, every centimeter equals a meter per second. So we could say 1 centimeter equals 1 meter per second. So in this case, this 7.5 centimeters would actually equal 7.5 meters per second. Maybe we're talking about two velocities that were added together. Now to get the angle, we would put a protractor on here, and we would simply measure this angle down here. So our final answer about our resultant, and we're saying the red one here is the resultant. We might say then that we had a resultant vector of 7.5 meters per second at 20 degrees northeast. Okay, here's our last example I'm going to work out for you. On here, it says we have this roller coaster. It's traveling at 100 meters. It's going 100 meters horizontally. Then it travels 40 meters at an angle of 30 degrees. So I would stick a protractor on here, and I would measure, and let's say that approximately is 30 degrees. So I would measure from here then 40 meters. And prior to this, I would probably take my ruler of some sort, and I might say that every centimeter equals 10 meters. So I'm going to say 1 centimeter equals 10 meters. So that means this would have to be 10 centimeters long. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we're saying this right here is 40 centimeters, or 4 centimeters, 1, 2, 3, 4. So now I've made that one be 40 meters, and I've got it at this angle of 30 degrees. So the question asks, what is the displacement from its starting position? Meaning, how far is it from its original position? Well, the red vector I'm drawing in here, the red arrow, represents the displacement. We would take our ruler, and I'm just going to draw in lines here right now, and we would measure it and find out that it's I'm going to say it's approximately 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140. According to what I have here, it is approximately 150 meters long, because I got it to be 15 centimeters, which gives me 150 meters at, now what I would do is I would probably take this protractor and move it. All right, I'm going to take my protractor and I'm going to move it over here. And I'm just approximating right now what this measurement would be. I'd actually measure it. We'll be actually measuring it tomorrow. And I might find out that this right here is a 15-degree angle. So I would say this is 150 meters at 15 degrees northeast. And that's how we'll be adding our vectors. Well, we've got two examples we've done here. I don't have any other that I'm going to give to you. So what I would advise for you is to go back and see if you can't work these, work this one now on your own. Pull it up, hit pause before I give you this problem, and try working it out without seeing anything. Or change the numbers. All right, change it to 120 meters. Change this to 30 meters, and then make this maybe 50 degrees. And see approximately what you come up to. Hey, I'll see you tomorrow. I can't wait to get going back with physics. I'll see you on the flip side.